Applications requiring machine vision continue to grow in the market, and engineers must decide on the right sensors for their designs. For many of these applications, simply giving our designs the ability to see the world around them is not enough, as we need them to understand the distances and features of objects around them in a way that 2D sensors can't achieve. What methods and technologies are becoming available to engineers to help us to meet these challenges? We've been talking a lot on The Current this season about machine vision applications and talking with industry experts in this area because I think it's such an important part of where embedded engineering is really going. And that over the course of the next few decades, our embedded systems being able to see and interact with the world around them is going to be critical in so many more designs. It seems to be going into so many market applications that we never really would have considered before. And so whether we're talking about maybe more of the common ones like vehicles and drones, and now where we're going with humanoid robotics with machine vision, they're really starting to kind of create this entire new area of embedded design, which is being dubbed physical AI. And I think that's going to be a really fun area for us as engineers to play in over the balance of this decade and beyond. And so I love talking with industry experts that truly understand this stuff. And so today I'm speaking with Steve Harris, who's the Senior Director of Marketing for Industrial and Commercial Sensing at onsemi, and someone that's really seeing this area evolve and do some great things. So Steve, thanks so much for joining us on The Current today.
Yeah, thanks for having me, Todd. Excited to talk about it.
So when I think about this area and what's going on with it, I look at what onsemi is doing. I look at what's going on in the market, and honestly, everything that's happening with physical AI and with machine vision, these are all the things that 8-year-old me was really excited about the world eventually looking like, and what got me to want to become an engineer, which is really exciting. And onsemi's got an amazing place, I think, when we're talking about image sensors. I think something like 8 of the last 11 Best Picture award winners have been filmed with onsemi sensors, which is absolutely incredible. You guys have an expertise here that really is recognized. What are some of the latest innovations that onsemi is looking at when it comes to image sensors?
Yeah, so great question. Thanks for the introduction there too. And yeah, I mean, even myself, as you mentioned, I've been in the industry for quite some time, roughly about 15 years of my career. I've been in image sensors. It's a cool space to be in, to be honest. So you see a lot of people that get in the image sensor space and they just stay there, whether it's a different company or they work in an end application. And it's just been exciting to see the growth. So now going back kind of to your question, what are some areas that we're trying to focus on? And I think really kind of when we take a look at it, what we're trying to do is we're trying to find good technologies that people seem to want to use, but maybe there's some hurdles or limitations that are kind of inhibiting them from doing that. One of the key technologies I'll just bring out right here is in our HyperLux ID family, iToF. So for example, ToF has been a very popular technology. People want to use it, but there have been a lot of limitations, specifically with indirect time of flight when it comes to calculating depth. So when we looked at that, we looked at an area that, hey, there's this great technology, but maybe the solution isn't so usable yet. And I think we did that. We took a look at it, analyzed it, and then figured out a way to really correct the technology and almost, I would say, enable it for the marketplace. So that's kind of where we're focused on, kind of looking for those areas where we can really bring technology enablers.
Right. And so, if I understand correctly, that integration of time of flight with the image sensor really takes your embedded system out of the realm of really just seeing the world in 2D and really understanding the depth of the world. Starting to see it truly in 3D, which is a really powerful thing when we're talking about many of these machine vision applications that we're looking at, to get our embedded systems to be much more capable, much more functional, which is incredibly exciting. I know a big part of that has been your HyperLux family of different image sensors, and I know that's kind of a broad range name for the overall family, but what are some of the other innovations within HyperLux that really set it apart from the competition?
So good question. And I will say this. So HyperLux is kind of the branding that we use for all of our image sensor and sensing technologies. Now, we have specific families within the HyperLux. So we have For example, we released about a year and a half ago Hyperlux LP, that's Hyperlux Low Power. We have Hyperlux ID, which we just press released in Embedded World this year, maybe just about a few weeks ago. That is focused on time of flight. So focusing on that one more specifically, so with the time of flight, as you'd mentioned, you're able to gather depth, and so that's just, pun intended here, an extra dimension that these machine visions can algorithms and neural networks can use to make itself more efficient. And when we took a look at this, there were, I would say, some significant hurdles to overcome with indirect time of flight. One of those was motion, for example. If you had an indirect time of flight of sensor, motion was a very difficult thing to capture very accurately. The distance at which you're able to do it, the precision and the accuracy. So there were a lot of elements there that really made it difficult to use in some machine vision type applications and other types of applications. And we took a look at that holistically and came up with a really good solution called Hyperlux ID.
And I think that's some really exciting developments. I think when you pair that with an acquisition that onsemi made late last year with SWIR Vision Systems, SWIR
Right.
Vision Systems, that's
Right.
really, really exciting, where we've got now the access to shortwave infrared technology, which tends to be a technology that I think historically we thought of for more expensive applications, applications like defense, like very low volume, industrial applications, things like that. And it's kind of been maybe cost limited to really go out into the white market in some ways. But with this new acquisition, my understanding is that you now have access to quantum dot technology, germanium on silicon, and that's going to allow us to have lower cost capabilities for these type of applications. Can you talk to me a little bit about what you guys are doing with shortwave infrared applications and how that's being used in the market today?
So, I mean, I think this is very synergistic with what I just said with kind of TOF here. Again, SWIR is another technology that has a lot of great uses and very applicable to a lot of machine vision scenarios and other scenarios. And you kind of hit it right off of the top there, right? It's just expensive. It's that's the number one hurdle to really making this more mainstream. So if you look at some of the solutions that are out there right now, they're using indium gallium arsenide, and then you mentioned silicon germanium. Those are technologies that are still going to remain fairly expensive. In addition to that, by the way, those type of technologies can extend the wavelength that you're able to detect light out to a level that actually puts you under ITAR, which is basically a trade restriction for those not familiar. So there was a technology there that had limitations. One, it was expensive. Two, it was bound by trade regulations. And I think our goal with SWIR Vision Systems and SWIR Vision Systems' goal as well is really to bring that and make it more economical. And you mentioned the quantum dot. It's called CQD, colloidal quantum dot. That's the technology that we believe is going to make this an affordable technology. And again, we're going to become hopefully a market enabler here for the technology itself.
Yeah, I think it really is an exciting area. So talk to me a little bit more about what are some of the applications that you're seeing really adopt this, and do you see it really an area of market growth for shortwave infrared in the market today?
Yeah, I think we're only at the tip of the iceberg again, just because of the inherent cost. But it's everything from device inspection, actually our own silicon inspection. Ironically enough, using our own sensors to inspect our own silicon. There are other military applications, but the longer wavelength light is able just to penetrate deeper. And so, and then of course you don't have visible light, right? So you're able to do it in complete darkness. So that's kind of where we're seeing it. It's a lot of still machine vision, robotics type applications, night vision, a longer wavelength penetration through objects, that kind of area.
Yeah, got it. And definitely some exciting stuff there. When we think about, this advancement and this expansion of
Yeah.
physical AI and the need for more machine vision and all these different applications, I think what you've talked about with the Hyperlux family, with what we have now with SWIR technology at onsemi, there's some really exciting things here. How, from your perspective, are you seeing that help to advance, the adoption, the capabilities, and really the innovation that engineers can do in their designs with onsemi technology?
Yeah, so here, let me give you just a classic example going back to the time of flight. So, volumetry. This is basically an application where the whole goal of the application is just to measure the volume or the box or some sort of objects that's coming through. So now you want to do that, then you have some options for measuring dimensions. You have stereo camera, meaning that you have two cameras kind of in a parallax situation. They need to be highly coordinated, highly calibrated. First off, you have two sensors. You have to, deal with the frame rate issues, etc. The other approach on doing the volumetry would be through kind of your traditional time of flight. Now, so going back to what I said with traditional time of flight, it had limitations when it came to motion. So one of the things that we've done on our Hyperlux ID family is we've enabled us to capture depth very accurately with fast moving objects. So now going back to my volumetry example, you have, let's say, a conveyor belt, and you put a box or you put an object on there, and it's coming down that conveyor belt, and you want to measure the depth of that. And, you could use that for whatever you like. How do you store it in a warehouse? Is it the right dimension? Are there dents? All different sorts of applications there. But going back to this, what people were having to do before to get that depth is they would have that box or whatever that object is coming down that conveyor line. And then all of a sudden, camera's on top, stops the conveyor belt line, takes a picture, gets the dimensions. Okay, so now you've just stopped your conveyor belt line. And I've seen examples where now customers have used our iToF, which does not have issues with motion. And I could talk a little bit later about some of the reasons why, but now you have our iToF, where now literally I've seen it where somebody drops a box on a conveyor belt line and it almost just flies right off the conveyor belt line. And yet we're gathering the depth information perfectly. So just a classic example right there of how we're making something way more efficient because of a technology that we were enabling. Before, again, that's a really kind of difficult thing, right? Where you have a conveyor belt and you just got to stop it. Another one, like, so you go to airports now. I don't know if anybody has seen this, but there are a lot of self checkout. So self checkout's becoming all the rage, and it just makes people more efficient, etc. Well, now I've seen it in certain places, not even just airports, but I even think grocery stores, where instead of actually scanning a barcode and then putting it into a bag, you set a bunch of objects on a plate, and then there's a camera sitting on top of it, and it takes one snapshot of all of the objects that are on that plate, and then sends that through, and then produces a full-on basically list of the items that you have. So now instead of scanning all of these things one by one, you just take all your objects, you dump it on a plate, boom, everything pops out right in the line. You confirm it, hit buy, you're done. So, I mean, it's just another element to really kind of enhance certain areas. So, and I can keep talking about this for a while, but another one, right? Maybe it hits home a little bit for me too, is, something that's called patient monitoring. So if you have people that are invalid, or they're, for whatever reason, they need to be monitored, memory issues. The way that that's been done right now is either through a security camera, or it's somebody actually just watching the person all times, right? That's really difficult, really inefficient. And furthermore, if you're taking images, we all worry about the privacy concerns. Time of flight. Okay, again, so now you have a patient. Keep in mind, so time of flight, we're measuring depth. That's it. But the way you can kind of think of what that output image looks like is it's basically going to create kind of a silhouette of the face, or whatever it may be, the objects that are in the room. And then it's going to do some depth measurement. But you're not actually looking at a physical image most of the time. So what you could do from that is still keep the patient privacy. So you're not having to look at physical images here. And then furthermore, you're able to determine what actions they're doing. So if somebody fell off a bed, or somebody standing up, or somebody's doing some sort of motion that maybe gives a signal that there could be some issues, that can be detected right away, done with privacy, and relayed right to a medical person to help out. So just three areas of just like small tip of the iceberg type examples of where depth is really enabling solutions and people to be more efficient.
Yeah, and like I kind of said earlier, I mean, it's amazing. The three applications you just gave, they're across three very different type of market applications, which just goes to show how many different areas of design this is touching now. And when I look at it, the value proposition that onsemi seems to be bringing to the table beyond what we see in other applications
Yeah.
is your ability to operate when the things that our embedded systems are looking at are actually in motion. Can you speak a little bit more to that, and,
Yeah.
and how onsemi is bringing value into that kind of an area?
Yeah. So there's a couple of there's really, it kind of boil it down to two different areas. So the first one is the type of sensor that we're using. So what we're using a global shutter sensors. So just quick explanation again for those not familiar. There are two basic types of operations of sensors. I don't want to really elaborate more, but two basic types, right? You have a rolling shutter and you have a global shutter. Your rolling shutter, the way that the process works is that you expose a row of pixels, you read it out. You expose a row of pixels, you read it out. You do that sequentially throughout the entire pixel array. So what that means, though, is that when you have motion, that first line is exposing, and every single line within that pixel array is exposing at a different piece of time. So inherently, if you have a fast-moving object, you're going to create motion artifacts. And what usually produces on the rolling shutter artifacts is, if you took a look at, if people like to out there, go Google it. But if you want to go look at like a helicopter turbine, or maybe a plane fan, you want to take a look at that, you'll see that there's like a curvature that happens kind of, and that's just the artifact that you get from that rolling shutter, because again, the first row of pixels and the last row of pixels are completely captured at a different period of time. Okay, so now imagine, again, going back to my example of trying to measure a box and the dimension of a box, and it's curved. Okay, so rolling shutter, difficult for this, but maybe still workable if it's not too fast of a moving object. So that's number one. Number two is the way that we're able to calculate depth with indirect time of flight, that is through phase. So you send out a light, you get the light bounce back, and then all of a sudden you're capturing 4 different phases. I'll just use that again as an example here. So, okay, now you've got 4 different phases. Now what you need to do is you need to process those, and keep in mind that, our sensor here, we have 1 million pixels, one megapixel sensor. The previous ones out there have been VGA, but again, that's a lot of data on an entire pixel array to calculate. So what happens is, if you don't have that depth calculation real time and done on board, you're having to you're having to read out every single one of those phases to a processor that's sitting discreetly from you. That processor then needs to store it in memory, and then it needs to do the data calculation. And even some of the higher end processors out there, that's a lot of data intensive work for them. But introducing that MIPI lag of reading out 4 different phases, having that stored in memory and calculated, is taking time. And again, so you had 2 limitations here. Now what we're doing with our solution, I mentioned the global shutter, that we're using the global shutter architecture. So on the first part of that, you don't have to worry about time delay from the first row of pixels to the last. So that's first. And then secondly, what we're doing on the readout architecture with the phases is that we're actually storing all of the phases inside our device itself, and then the processing is actually done locally. So our processing is happening at real time with the depth calculation, and then combine that with the global shutter, and now you've really solved kind of that motion issue that was a burden before.
Right. And I think that's an incredibly powerful way of doing it. I think if you can get away from the need to send that image data to a processor or have it processed somewhere else and then send that back,
Right.
that's incredibly challenging. So the way that you're
Yep.
doing that for the engineer and the design earlier on,
Yep.
what a powerful thing. To get designs up and going. So, next question, maybe I'll tee it up a little bit for you. What are some of the major challenges that you're seeing engineers that are trying to integrate an image sensor into the designs dealing with? And again, I'll tee it up a bit and saying the question I get asked a ton is what's that inflection point from going with a chip down image sensor versus using a module? And what are the things that engineers should take into account when they're considering making that decision?
Yeah. So, I think that image sensors are inherently difficult to work with because it's not your standalone semiconductor. I mean, it relies on many different components to really come together seamlessly. And if they don't, if there's one component in that imaging stack, whether it be the optics, the sensor itself, the interface to the processor, or the processing, or even the software on top of that, there's a link break there. So now, if you think about that, kind of going back to your question here, if you're a designer at a medium size or smaller size company, you may not have the equipment to actually do a full blown module or full blown design. So that's one part of it. Certainly, aligning the lens to the actual sensor properly is not a simple thing to do. So, that requires some enhanced technology to do it. But furthermore, getting all of those elements in line in a stack is pretty difficult. So what we're seeing are a couple of things. One, we work with Future, for example, and you provide your imager access module, where basically you're actually providing a form fit function module to a customer. So you take away that one element of how do you align the lens to the sensor, and you give a module, and okay, it's coming out with an interface, and you've already got that defined. Now you just need the processor. So I think that's one way. So for middle, low volume customers that don't want to deal with modules, they can come to Future and say, "Hey, we like this sensor. Do you have a module for that?" And you guys do. So that's a great part about being, on the Future, Future onsemi relationship here is we have that ability. Now, secondly, the other thing we can do too is we can also provide good references. So if in this state, our customer does want to do something a little bit more specialized, of course, if it comes off the shelf, right, they kind of have to live with the limitations of that. But we can do something a little bit more special. If they want to do something a little bit more specialized, we can give them a reference module. We released this concept called PRISM. It stands for Premier Reference Image Sensor Module, but it's just basically a reference. There's no IP in it for us, but it kind of guides the customer on how to design a module. Or, for example, if they want to come to Future again and they want to buy a module from you, maybe we can give this as a reference, right? So that's kind of one element that we can do too, is again give off that so that the customers that don't have a lot of experience, they at least have a reference. So that's the second part of it. And then the last part of it that I think, in all honesty, is really the most difficult part is really the image sensor tuning. And that's where, people that do image sensor tuning are needles in a haystack. They are really specialized engineers. Not easy thing to do. So for us on the ecosystem front, it's really important for us to work with our processing partners. And if we don't, I'll throw out Renaissance, for example, NXP. If we don't work with those processing partners to do that tuning in advance, that means the customer's got to do it, or they have to hire somebody to do it. Also, not an easy thing. So for us, hopefully we're working ahead of the game too. We're before the silicon really gets released to the mass public. We've already worked with the processors. And so then it's already in that processor library of tuning, and maybe some customers can do some specialization. So there are things that we're doing on the hardware side to get people up and running quickly. There are things that we're doing on the software side that we're helping people to get up and running quickly. And what that really helps is the mass market and these kind of mid-tier, small-tier customers that just don't have the engineering know-how or the resources to do it.
Yeah, and I know between Future and onsemi, we absolutely want to make those resources available to our customers. So when it comes to doing a design with an image sensor, that process of just tuning it and getting the driver up and running, all of that adds a significant layer of complexity to the design that, a lot of us as engineers, if it's our first time doing it, we don't have that experience. And I think between onsemi Future, we can bring that expertise to the table. For example, we just were working with one of your AR0830 image sensors and interfacing that with an item X8. So our team of engineers, we have image processor or image sensor specialists. We have processor specialist engineers. That's all they do. They had to work really closely in conjunction with each other to get that application up and running, to get it tuned just right, and to get it working. And it took a little bit of time, but that's something that we found is really an expertise that we have, and we can help other engineers with, and we want to bring to the table. So whether we're looking at interfacing an image sensor with a processor from ST, Renesas, NXP, or others, we can really help to bring that to the table. And I know that's something that onsemi also wants to join us in.
Yeah, and I'll say this too. I mean, the initial rollout in doing that, there is a steep learning curve. And I know Future had seen that steep learning curve, and we've kind of lived it with you guys. But now once you get over that steep learning curve and you kind of figure out, hey, this is how it works and this is what we need to do, then it starts to become more repetitious, and you're kind of already at that level right now. So that gives, our customers that are using Future a huge leg up, because you guys have already climbed that steep learning curve, and, you're at a level you can do this now pretty efficiently.
Yeah, absolutely. And, with Future, we're ready to be the Sherpas and help guide engineers up that mountain. We've already made the trip a couple of times ourselves, so we can kind of help to steer them in the right direction with everything that's going on. And, I think with what onsemi is bringing to the table, from your Hyperlux that we've talked about, the Sweer families that we talked about, some really exciting things that are going to be happening in the market. So whether customers are looking at drones and machine vision and vehicles and humanoid robotics and all these amazing areas of high growth, it's going to be a really exciting time as we see all of these childhood dreams, finally coming to life for so many of us as engineers, and we move forward into what I think is going to be a lot of fun in this design space.
And I'll tell you this too. I mean, I'll tell you this too, Todd. So we'll always bring iToF out for a demo, just even to any customer that maybe says, I never thought about it. Because maybe, they shelved it in the back of their mind as technology maybe they just didn't have access to because they had some sort of limitation. And so we brought it out to customers that we weren't sure that there was really an application for. And all of a sudden we said, well, hey, you know what? If we give you a kit or we sample it to you, what do you think? And maybe there's something you could do to it. And so we've come up with ideas like 3D video conferencing and just all other sorts of things that, man, we never even thought about when we created the device. So that's also been really exciting to see too. It's this technology enabler that, even some things that we haven't thought about, maybe our customers have, but they just said, hey, we can't use the technology right now. And I think we're at that point now where the technology is really enabled. So it's been exciting.
Yeah, it is a true area of engineering innovation and really at the bleeding edge of what we're all trying to accomplish, which I think is where design is always the most fun. So absolutely incredible. And this machine vision and the parts that onsemi brings to the table really are the perfect Lego building blocks, for I think really creating the applications that we need in this machine vision space. So Steve, thanks so much for joining me on The Current today. It's an absolute pleasure, getting to hear a little bit from what you're seeing in the market and where you see this going. Really, as I've said, a very exciting area of technology for me. And to our audience, thanks so much for joining us on this episode of The Current. We hope you got something out of it, just like we have in this conversation. If you have an image sensor application or any other embedded systems application where you'd like to talk to some other engineers, maybe get another set of eyes on it, bounce around some ideas. We at Future Electronics would absolutely love to talk to you and help you out with that. Please feel free to reach out to us at any time at Shaping the Future. That's one word, Shaping the Future at futureelectronics.com. And some of our engineers would be happy to talk to you. I'd be happy to talk to you about the designs that you're working on. Thanks so much for joining us on this episode, and we'll look forward to seeing you next time on The Current.